All right, now this is not a new lesson. In this one, we're just going to practice some problems to kind of work out the kinks and look for some issues that sometimes cause people problems. So here's what I want you to do. Let's look at this first one. I've got this nice table with 3 substances and specific heat. I want to know which of those 3 substances would require the least amount of energy absorbed to reach 100 degrees Celsius from room temperature. We'll say room temperature is 25 degrees Celsius. Once you've picked out which one of these would require the least amount of heat to get it up to 100, I want you to calculate, well, how much heat would it take to get from room temperature 25 degrees Celsius up to 100? And then type in your answer to both what's the compound and what would be the amount of heat needed. Okay, so here's what I got. I got, well, since calcium carbonate has the smallest specific heat, it requires only 0.82 joules per gram. Ooh, they're using gram Kelvin instead of degrees Celsius, but we know it's the same thing. Anyway, it requires the least amount of heat to go up by 1 degree Celsius, and so therefore it should require the least amount of heat to get up to 100. So I plugged in Q equals MC delta T. I got 2,000 grams, right? Did you catch the unit conversion? Used the 0.28 and did final minus initial, and I got, it's going to take 123 kilojoules. Did you catch the kilojoules at the end? Now, I'm not standing by my sig figs at all here. I feel a little bit, well, it's not just the fact that there's only 2 sig figs on the kilograms. I wish I'd put a dot there after the 100. I mean, technically there's only 1 sig fig, and that means we're not certain even in that place. So when you did this subtraction, you would actually get down to essentially completely uncertain. So I wish I'd put the decimal there. So we'll ignore sig figs here. All right, on to the next one. Okay, I have a table of specific heats down here. And what I want you to do is determine the molar heat capacity of copper given the specific heat. And then determine the heat capacity of 300 grams of copper. Okay, so here's how I tackle it. The problem is that we know the copper in joules per gram degree Celsius. I would like this to be in moles at the bottom to get molar heat capacity. So here's what I'm going to do. Ooh, it went away for a second. I do the specific heat capacity, and remember it's joules per gram degree Celsius. So I'm going to need to multiply by the molar mass so that the grams cancel, right? If I get my grams to cancel, I will get moles in the denominator, and I'll have joules per mole degree Celsius. So there we go. And then if I want to know the heat capacity of 300 grams of copper, well, you can see I can multiply by 300 grams of copper times the specific heat capacity. That cancels the grams, and I'll be left with the heat capacity, which is just the joules per degree Celsius. And I get 114 joules per degree Celsius. Now I'm bringing these up because I'm almost 100% sure WebAssign is going to ask you to find the molar heat capacity and the heat capacity of a specific amount of stuff. And if that's true, that's how you tackle it. All right, let's do one last one, which has to do with calorimetry. So you can read the question here. I want you to calculate the specific heat of the metal. Okay, well, I'm going to use the system and surrounding strategy. I'm not going to list my data because I'm going to go with the setting the equations equal to each other. But remember, the key to doing this is you got to have this negative sign in here because the heat absorbed by the water is the heat lost by the system. So you have to have a negative sign in front of that one. When you do that, the mass of water is 250. The specific heat of water is 4.184. And remember, final minus initial. Then the other trick is when you do the metal, we know the mass, we're finding the specific heat. Remember, the final temperature here is the same as the water because the water went up in temperature, the metal came down, and where they met is the same. So you subtract those two. Being very careful because you can see you're going to get a negative here. You've got that negative out front. That takes care of it because specific heats should always come out to be positive. So 0.406 joules per gram degree Celsius. I think I was a little bit more careful with sig figs here, although maybe not. Let me get a different pen color. Let's look at sig figs. When you subtract these two, you're going to get 3.3 degrees Celsius. Ooh, we're down to 2 sig figs because you remember subtraction, we got to keep it to the tens place. Here we do 18.3 minus 75. I don't even really know what that is. What's 18.3? And did it really say? 75? It's negative 56. Did it say? It did say 7.0. So we're going to get negative 56.7. So we've got 3 sig figs there, 4 sig figs, 4 sig figs. It looks like this is going to be the limiter. I should really drop this down to 2 sig figs, 0.41 joules per gram degree Celsius. All right, very good.